All right, up next we have a multiple choice question here from an old AP test. And so a rock is dropped from the top of a cliff. 1 second later, a second rock that is twice as massive is dropped from the same cliff. Ignoring air resistance, which of the following statements are true, select the two best answers. So what I'm going to do is I'm going to go through each one. And this is a lot of times a good idea, each one at a time, and try and figure out whether or not each individual statement is true. So the rocks hit the ground traveling at the same speed. Well, thinking about energy here, all right, I'm starting with gravitational potential energy. I'm ending with kinetic, so I can say mgh equals 1/2 mv squared. And as happens often, the mass cancels out. And we see that energy-wise, all right, it's going to show us that the velocity is going to be the same for both. They're dropped from the same height, so they will hit the ground traveling at the same speed. So that part is correct. All right. B, okay, selection B, they hit the ground with the same kinetic energy. Well, we know that kinetic energy is 1/2 mv squared, and we just showed that the velocity is the same. However, their masses are different. One is twice as massive. All right. So that's going to mean that they can't possibly hit the ground traveling with the same kinetic energy. So that one is false. All right. The rocks hit the ground more than 1 second apart. Well, they start 1 second apart, and it's going to take them the same amount of time to hit the ground, right? And that really, we can't necessarily answer questions about time using energy, but we can with kinematics. So if we think about kinematics here, all right, they both have the same initial velocity. They both fall the same distance, some height that we don't know, and they're both accelerating at the same rate. All right, all these things are the same, which means their time in air is going to be the same. So if they hit the ground, all right, or if they start out 1 second apart, they're going to hit the ground 1 second apart. So this one is also not true. The last one, the distances between the rocks increases as they are falling. This one we obviously can say is correct by process of elimination, but if we think about it, all right, 1 second later, all right, 1 second after the first one is dropped, the second one is dropped, and they're going to be some distance apart. But here's what we know. We know that the one that's just being dropped is currently moving at 0 meters per second, right? The instant it's dropped, it's not moving. The one that has been falling for a second is already moving down. So, since this one is moving faster, that means, yes, these distances will increase. Okay, so this one is also true, so our answers are A and D are the correct answers. All right, a car is traveling at a speed of V, skids to a stop over a distance of X. If the same car was traveling at twice the initial speed, how far would it skid before coming to a stop? So, this is one where we're going to set up our energy, and we're also going to set up two situations. We're going to set up our original situation, and we're going to set up our new situation, because we want to compare the distances that each car would take to stop. Alright, so of course we're going with E initial plus work equals E final for both of them, and for both cars, they're starting with kinetic. Some work is being done by friction, that's what's bringing them to a stop, and they end with 0 energy. So we can fill in what we know about each one of those energies, 1/2 mv squared plus the force of friction times x, that's our distance for the original, times cosine 180 since it's friction equals 0. And for this one, same thing, 1/2 m. Now it's going to be 2v, that entire quantity squared, plus that force of friction, okay, which wouldn't change, by the way. All right, just because the car is traveling faster, friction doesn't change. And then we're going to have x prime cosine 180 equals 0. All right, so I'm going to go ahead and simplify these two equations. I know that cosine 180 is -1, and so I can move that ff times x to the other side, and I can solve for x. And so I really end with these two equations here, 1/2 mv squared equals ff times x, and 1/2 m times 4v squared, remember we have to square the 2, equals ff times x prime. I'm going to solve for x and x prime, and you might see here that the only difference really is that 4. You might be able to jump to that conclusion, or remember we can always divide those two equations. So 1/2 m times 4v squared over ff all over 1/2 mv squared over ff. and that's going to be equal to x prime over x. I give myself a little bit more room here, and remember that dividing by that double fraction is the same as multiplying by the reciprocal. And this is what we're left with, and the 1/2 and the m and the ff and the v squared can all cancel out, and so what we're left with is 4 equals x prime over x, so 4x is equal to x prime. All right? And if we think about our original answer here, that means that this is answer A, 4 times as much. All right, moving on to this next one, we have a longer AP style one. A block starts from rest at the top of a hill and slides frictionlessly down the track with a radius of r as shown. What is the minimum speed the block must have at the top of the loop in order to remain on the track? So this one, we're actually thinking about a block going around a loop, going around a circle. So hopefully this triggers some stuff you remember about circular motion here, because that's where we want to start. So I'm going to start with my forces acting on the box at the top of the loop. So I know that I have the force of gravity acting on it, and it's accelerating inwards because it's traveling in a circle. And we're thinking about this minimum speed piece, all right? And so I remember that that minimum speed is the point right before the box is about to fall off the track. So I can say that there is no normal force, all right? So I'm going to go ahead and set up my F equals ma. All right, so I have the force of gravity is equal to m times v squared over r, right? Our acceleration due to gravity when it's traveling in a circle. So I can say mg equals m times v squared over r. The m's cancel. I multiply both sides by r and take the square root, and I find that my velocity, the minimum velocity I must have, is the square root of g times r. Alright, so for the next part, I'm looking for the minimum initial height of the hill above the ground that will allow the block to remain on the track. Alright, so really now I'm thinking about energy, right? I'm starting here at the top of the hill, okay, at some height, alright, and I'm going to this point here where I must be moving with this velocity. So I'm going to set up my energy equation. So what I have energy-wise is I'm starting with gravitational potential energy here. Okay, there's no work being done because we know the track is frictionless. As I'm going through and I get to the top of that loop, I have gravitational potential energy because I still have a height, and I have kinetic. So I'm going to fill in the equations that I know. So I have my equations. I know my mass here will cancel, and I can put in some of the things that I know. I know my velocity here. Okay, and I actually know my height. If I think about this circular loop, the height is simply the diameter, or 2 times the radius, so I can substitute that in as well. So we have here g times my initial height is equal to g times 2r plus 1/2 times the quantity gr squared. I'm going to simplify a little bit. I see here that my gravity, my g terms actually also cancel out, and what I'm left with in the end is that the height is 2r plus 1/2 r, or 2.5 times the radius. Okay, and that actually wouldn't even matter if this took place on another planet. We see that that g term cancels out, so that's not even going to affect it. All right, for part C here, we're talking about this idea of a circular loop, okay, which looks something like this, versus a clothoid loop where it almost looks like a little teardrop. All right, and most roller coasters use this clothoid loop, and we want to think about why that might be true. Okay, so we want to explain that, why it's advantageous to use the clothoid loop. And I'm going to paraphrase all the major points that we need to touch on, but the biggest thing is that the clothoid loop, the radius is smaller at the top of the loop. Okay, so that's one thing we notice, right? The radius here is not a constant radius, right, at the top of the loop. So what does that mean? Why does that matter? Well, we just found that the velocity needed to stay on the track is the square root of gr. So the fact that the radius is smaller means, okay, a smaller velocity will allow the cart to stay on the track at the top of the loop. All right, and this really means that the heights of the hills can be smaller because we don't need quite as much speed. Okay, so that's the key there. All right, moving on to our last problem here. So we have a block initially positioned at x equals 0 is in contact with an uncompressed spring of negligible mass. Block is pushed back, all right, from this at rest point back to this position D, so that's how far the spring is compressed. And then the block's released, so it slides back to its initial point, okay, and then it comes into contact with this section of the track where we have friction, okay, eventually comes to rest here at point 3D. And so what we want to do is we want to sketch the energy of the cart, okay, starting here at negative D past our 0 point, okay, and going all the way to this point 3D. So two things to keep in mind here with this, all right. When you're doing these graphs, I think it's really useful to think about, number one, the energy at the beginning and at the end. Any point where we know the energy, we're going to plot those points first, okay? Number two, it's useful to think about what the relationship is between that distance, okay, and that energy. So I'm going to start here thinking about my two equations. So spring potential energy is 1/2 kx squared. Kinetic is going to be 1/2 mv squared. So I'm actually going to start with my spring potential energy, and the reason is I know that that's what we ultimately have at the beginning. I know we're going to start with some amount of spring potential energy. So I'm just going to say it's 4 blocks high. It doesn't really matter what you say, but it will matter later on, but your initial amount does not matter, okay? I also know that once we get to this point here, there's no more spring potential energy. The spring is no longer compressed any distance. And so that spring potential energy is just going to ride along this x-axis here. All right. Because it's going to be 0 the whole time. Now, in between these 2 points, how do we get from here to here? Well, I see that spring potential energy and distance have this quadratic relationship. So this is simply going to be part of a parabola, something like that. So there's my spring potential energy. Now, my kinetic. Things I know about my kinetic. Well, I know we start with no kinetic because we're at rest. I know that at this 0 point, okay, all of my spring potential has become kinetic. And I know that by the time I get to the very end here, I'm down to 0 kinetic. All right, so let's think now about how we get from one point to the other. Well, we have this flip relationship between spring potential and kinetic. So this curve here for our spring potential, our kinetic is going to follow that, just flipped upside down. So it's going to look something like this, okay? And if we look here at some of our points, right, that's the point where they have the same amount, and that makes sense where they intersect there. All right, we have 2 blocks of kinetic, 2 blocks of potential equal to our initial 4. All right, and we can do the same for other points. It might not be exact, but it's going to be a close approximation. So that's what that kinetic is going to look like up to point 0. Then we are losing energy, and the reason we're losing energy is because of work, F delta x cosine theta. So the work done, the energy lost, is going to have a linear relationship, okay, with the distance. So this is simply going to be a downward sloping line taking us to that final point. And that's what our graph's going to look like. Okay, now for part B. All right, we have the situation where the spring is compressed twice as much, okay, so to a distance of 2d. A student is asked to predict whether the final position will be twice as far at 60. And the student says yes. We're compressing it twice as much, it will have more energy and therefore will stop at 6d. So we want to think about not necessarily whether or not the whole statement is correct, okay, but whether or not individual parts are correct. So first we want to think about what aspects of the student's reasoning, if any, are correct. So it is correct here that the box will have more energy, okay? Spring potential energy is going to increase as the distance increases. So there will be more energy. That part is true. And we can really think about the fact that US equals 1/2 kx squared. Now for the second part, which aspects of the student's reasoning, if any, are incorrect? All right. Well, we want to think about this second piece. Will it end up at 6d? Okay, so the box will not end at 6d. And here's why. is the energy, and we don't necessarily have to say what the new energy will be, but the energy will not double because, okay, the energy is proportional to x squared. So when we double that distance, okay, it means that the energy will not double. It will be some other factor, and we'll find that in a second. Okay, moving on to part C here. Now we want to quantitatively, with numbers, figure out how far the box is going to slide in terms of that distance d. So, two things I'm going to do here. Of course, I'm going to think about my energy. All right, E initial plus work equals E final. And I'm also going to set up an original and a new equation here. In both cases, we're starting with spring potential energy in the very beginning. We do have some work being done by friction, and although we are converting to kinetic in between, we end with zero energy. That's true for both. So for the original situation, it's going to be 1/2 kd squared plus ff times 3d equals 0. Okay, and for our new equation, it's going to be the same thing, but we're going to have 2d as our distance, and we're not going to know how far it slides. So I'm going to go ahead and simplify those two equations. I'm actually going to divide them just the way they are now. All I did was move that ff times displacement over to the other side. When I divide those two equations as is, the 1/2s cancel, the k's cancel, the d squareds cancel, those ff's cancel, and what I'm ultimately left with here is 1/4 is equal to 3d over x. I cross multiply and I find that x is 12d, 12 times as much, which makes sense because we quadrupled the energy, okay? So it makes sense that it would take 4 times the distance to bring it to a stop with that frictional force. Right. So the last one, basically the question is asking for us to link our two parts, part B and part C. So how any correct aspects are identified in part B by the mathematical relationship, and how any incorrect relationships were shown by the mathematical relationship. So for the correct ones, all right, we had said originally in B that there is more energy. Okay, so there is more energy with the displacement of 2d, and we see that because our spring potential energy is 1/2 k times 2d squared, or 1/2 k times 4d squared, which is more than our original energy, which was simply 1/2 kd squared. The incorrect parts of this, well, we ended up getting a final answer of x equals 12d, okay? And again, we kind of talked about this. Number one, that obviously is more than 6d, but the energy we showed, that initial spring potential energy, is 4 times as much. Okay, so we need 4 times as much distance to take that energy away through work. For this next one, which is actually from the 2017 AP Physics exam, we have a situation where a class is asked to design a low friction slide that's going to launch a block horizontally from a table. All right. We see the two designs here from each one of the teams. We notice a few important things. They both start at a height of d above the tabletop, and they're both launched from a height of h eventually above the ground, but there's this weird thing where the table for 2 is a little bit lower. So that means that ultimately the initial height of 2 is just under the initial height of 1. Okay, but they do launch from the same height above the ground, and they do both launch horizontally. So the first question is, we want to know if they're released from rest at the top of their slides, do they land the same distance from their tables, yes or no? The answer to this question is going to be no. We now need to go about justifying it. So a few things we're going to think about. We're going to think about A, the fact that they're launched from the same height horizontally. That's an important piece. But also the fact that they really didn't start from the same height above that launch point. And we're going to think about energy for that. So the first point I would make would be that block 1 started from a greater height above the launch point. It started a distance of d above the launch point, whereas block 2 started D above the table, but its launch point was above the table, so it started less than D above the table. That means that the gravitational potential energy that block 1 has initially is greater than the gravitational potential energy of block 2. So when they leave the tabletop here, or leave the ramp, block 1 is going to be traveling faster than block 2 because it had more gravitational potential energy that got converted into its kinetic energy. The second point we need to make then is the fact that they're launched from the same height, which means that their time in air is going to be the same. They both have the same initial y velocity, same height, so their time in air will be the same. So the one that was traveling faster, block 1, is going to travel a greater distance than block 2. Moving on to part B here, the first part of part B. We now have a new setup where the blocks are both released from the same height. Okay, so they start with the same gravitational potential energy. They both launch from the same height. And so we want to know which one lands further from the respective tables now. And the answer now is they land at the same location. And really, it's just we've taken away that key difference that made them land at different spots, which was that one started at a greater height than the other. So when we're explaining this, I would just say that the blocks start with the same gravitational potential energy, and they therefore leave the table with the same kinetic energy, so they're traveling at the same velocity. Since they're launched from the same height, that means they're going to travel the same horizontal distance and be in the air for the same amount of time. For the second part of B here, we want to explain which block hits the floor first. That is going to be block 1, and the basic reason here is if we look at the shape of these ramps, okay, block 1 is steeper initially, okay, which means that block 1 is going to have a greater initial acceleration, and therefore it will get to the end of the table first. So to explain this, I would just say that the ramp is initially steeper for block 1, which means it will have a greater initial acceleration, and therefore it will reach that speed that it has at the end of the ramp faster in a shorter amount of time, and that means it will then fly through the air first and hit the floor first.